Hello everyone. In this video, we're going to learn how to sketch functions using calculus. So we're going to graph this function x to the 6th power plus 6x to the 5th. So first thing you want to do is maybe think about the domain of the function. So the domain of this function, it's going to be all real numbers because this is a polynomial of degree 6. So everything makes sense. Therefore, the domain is all real numbers, which means that there is no asymptote. So there is no need to use a technique to find asymptote for this given function or equation. So we know the domain is everything. Now let's go ahead and find the x-intercept. So the x-intercept is when y is equal to 0. So you set y equals 0. And you get 0 is equal to, I'll factor out a common factor on the right side. That's x to the 5th. And then x plus 6. So that gives me x equals 0 and negative 6. So there's two x-intercept for this given equation. We have 0, 0, and we have 0, negative 6. So these are the x-intercept. Let's hold on to these. We'll put everything together in a graph. And now let's go ahead and find the y-intercept and see if there is any. There's two x-intercepts. So for y-intercept, we're going to set x equals 0, and that gives you y equals 0 to the 6th plus 6, 0 squared. Sorry, 0 to the 5th. So when you do this, you're going to get 0. So 0, 0 happens to be x and y-intercept. And of course, we know that if the graph passes through the origin, it's going to be both x and the y-intercept. All right, now let's go ahead and find any critical numbers. So critical numbers is next. So for critical numbers, we're going to take this first derivative and set it to 0. So y prime is going to be, so I take the derivative of this function. I get, using power rule, you will have 6x to the 5th plus 30 x to the 4th. So that's the first derivative. Now we're going to take the first derivative, set it to 0. That will give you, now again, if you want, you can pull out the common factor. I'll put out only x to the 4th. Then you have 6x plus 30. So I set it to 0. I get 0 equals x to the 4th and 6x plus 30. So that means x is equal to 0. And if I set 6x plus 30 to 0, I will get x equals negative 5. So there are two critical numbers. Now we're going to test the first derivative around these critical numbers. So let's plot them on the real line and test the first derivative. So you pick a test value and you plug it into the derivative, the first derivative. So from negative infinity to negative 5, I can test negative 6. So let's pick that one. Negative 5 to 0, we'll pick negative 1. And 0 to infinity, we'll pick 1. So plug this into your derivative, that's right here, and see if it's positive or negative. So I have y prime at negative 6. That's going to be negative 6 to the 4th power, 6 times negative 6 plus 30. Now let's estimate. Well, a number to a 4th power, that's always positive. And then negative 6 times 6, that's a negative number, plus 30, that's going to be a negative number. So we get a negative sign for this interval. And you do the same thing for the rest. So for y prime at negative 1, we're going to get negative 1 to the 4th, and then 6 times negative 1 plus 30. Again, you estimate. The plus parentheses will always give you positive because it's even power. The second parenthesis, in this case, it's also positive. So the product is positive. And the last one, if I plug in 1, so the derivative at 1, so we're testing 0. So at 1, we're going to get 1 to the 4th times 6 times 1 plus 30. And of course, all of this is positive. So positive here. So you know that negative means you're decreasing, positive means you're increasing. So let's go ahead and write those out. So we know that our critical numbers are negative 5, and 0. So we're decreasing here, increasing here, and increasing here. So increasing, so the function is increasing from -5 all the way to infinity. And it's decreasing on the interval only -infinity to 5. So we'll always put this down. And now, because the sign changes around this critical number, we have either a maximum or minimum. So think about it this way, because you're going from negative to positive, so you have going down and then going up, so you have a local minimum. So we see that there is no local max, but there is a local minimum for this function, and that occurs at -5. So we want to find the value y of -5. That's going to be plug this into the original function, and that's all the way up there. X to the 5th, sorry, x to the 6th plus 6x to the 5th. So that's going to give you -5 to the 6th plus 6 -5 to the 5th. And you'll get about -3,125. So that's the local minimum value. So we'll put that together as well. Now let's go ahead and test the second derivative. So now we're looking for possible inflection points and concavity of this given curve. So we take the second derivative and we set it to 0. So the second derivative of this function, well, let's go to the first derivative. So the first derivative happens to be, so for this part, I'm going to be using this one because it's easier to differentiate, but factored, it's easier to find zeros. So if I take the second derivative of this, I get 30x to the 4th. So we'll get 30x to the 4th. And I want to differentiate the second term, that's this one right here. I'll get 30 times 4, that's 120. So that's plus 120x to the 3rd. And I set it to 0. So that will give us, so again, I want to factor out the common factor. Let's just factor out x cubed. Then you have 30x plus 120 equals 0. So x cubed equals 0 means x equals 0. And 30x plus 120 equals 0 means x equals -4. So these are the possible inflection points. Let's call them IP. We need to test the second derivative to determine if they are inflection points or not by simply looking at change in concavity. So I plot them on the real line again, and then we do the same thing that we did for the first derivative, but now you're plugging this test values into the second derivative. So keep that in mind. Now continue on. Let's pick a value in this interval. -5 is a good number here. -1 is a good number here. And then +1 is a good one here. So these are the test points we're going to plug into our second derivative. So for testing, I will grab this one because it's factor. It's easier to determine the sign. So let's go ahead and do that. So we want to find the second derivative of -5. We want to find second derivative at -1. And we want to find the second derivative at 1. So if I plug in -5 into here, I get negative number. And then when I plug in -5 into this x right here, I get negative number plus 120. It's going to be a larger negative number. So we get negative number right here, which means the product is positive. So this interval positive. When you plug in -1 into the second derivative again for these places, you get negative, and then so here negative and positive, so that's going to be negative. So this interval is negative. And the last interval, we're testing 1. So you can see that the second derivative is going to be positive when you plug in 1 here and here. All right, so done with that. So now because the concavity changes, so positive means you're concave up, negative means you're concave down. So we have change in concavity. That means these are indeed inflection points. So check, these are inflection points. That means you need to find their values, so you plug them into the original function. So let's write down the interval of concavity. So we are concave up on the interval -infinity to -4 and 0 to 1. That's where the second derivative is positive, and concave down, that's going to be only -4 to 0. And we have inflection point. So let's find them. So y of -4. So plug -4 into the original function, and you will get about, let's see, if I plug it into the original function, so that's x to the 6 plus 6x to the 5th. So you have -4 to the 6th plus 6 -4 to the 5th. That will give you about -2048. So that's one of your inflection point. And the second inflection point is at 0. When I do this, well, I simply get 0. So that's easy to compute. So there will be inflection points at these coordinates. Now let's put all of this together in a graph. So let's do our best to come up with a sketch. So here's my XY plane. And so the first thing I'm going to do is plot my intercepts. So my intercepts are right here. So we know there is x-intercept 0, 0, and 0, -6, y-intercept 0, 0. Let's put that down together. So 0, 0, and maybe I should use a different color to show. Let's show this one. All right, and then let's call this one -6, 0. And then we have, so we know critical numbers were -5 and 0. So let me just make our life easier by taking this to the bottom. So I'm just gonna take this to the bottom. So we have it right next to the graph. So we know that, so I'm gonna use some grid line to help us graph this. So -5, let's suppose it's right here. So I will erase them later. I just wanna coordinates this graph as much as I can. And then at 0, we're also splitting it up. And now let's take a look at the second derivative test. So this was the first derivative test. And now the second derivative is right here. That was concavity. So I will also take this downstairs and analyze it. So you want to put the first derivative and second derivative always kind of together, so that way it's easier to work with. And then we want to now split the real line into inflection points. So we have -4 right here, and then at 0. Okay, I'm just going to draw another grid like this to show the direction. All right, so this is good enough. So we know that our first derivative gave us a local, we had a local minimum at -5, which is -312. So let's put that right here. So -5 gave us -312. That's somewhere right here, all the way down here. So that was -3,125. That's a local minimum. And then we also have an inflection point. So there are two of them. So at -4, -2048. So -4 maybe right here. Inflection point, -2048. And the inflection point at 0. So we're increasing, looking at the first derivative right here, we're increasing from -5 all the way to infinity. So this portion right here, this is increasing. So you can think of your curve always going up. So always going up, something like that. Imagine that. And then on the left side right here, you're decreasing. That's what the first derivative tells us. So it's going to be going down this way. Now, because it's also concave up, we want to fill that in as much as we can. So I will start drawing now. So I'm decreasing and concave down. So it looks like I'm hitting the y-axis, concave up, and then I'm gonna hit my local minimum, and then still concave down. I start to change concavity right here at -42048. I start to concave down, and then I start to change my concavity at 0, and I have to increase and concave up, so something like that. So this is how the graph should look like, roughly sketched. This is y equals x to the 6th plus 6x to the 5th. So that's the graph. So you can see that, so this is change in concavity, inflection point. And here also change in concavity, inflection point. If you analyze the graph from here to here, you're concave up, which we see it. So it's kind of like a happy parabola. So concave up. And also if you look from here to here, you're concave down. And then from 0 to infinity, again, we're concave up. And from all the way from here to here, we are, oh, sorry, not all the way there, but from here to here, we're decreasing. And then from here to here, you're increasing, and then you continue to increase. So that's all of it put together in a graph. And of course, for the final sketch, you don't need this grid. I just have them so that it helps me to scale my graph in a way that I can label inflection points and increasing, decreasing, all of that. All right, so I hope this makes sense. Take care.